Hey folks, welcome to part two of the tutor's guide to exponential and logarithmic functions. I've recorded a nice long 42-minute video on a bunch of solving stuff, but unfortunately that doesn't address graphing. So we're going to use the highly sophisticated video technology here that is me creating an MS Paint graph to write on top of in a picture view. So apologies for the relatively low quality. Obviously, I'm not real savvy to the video production stuff here, but we're going to talk about how to graph exponential functions and then how to graph logarithmic. So considering it's something we completely overlooked, let's start with the very basic, the classic y equals 2 to the x. Now, if you don't know what something looks like in terms of a graph, the easiest thing to do is to plot out some points. So let's think about what numbers we can use. So we're going to plug in a 0, we're going to plug in a 1, we're going to plug in a 2, and then we're going to go a couple numbers in the other direction. So let's think about this. 2 to the 0. 2 to the 0. What is 2 to the 0? Any number to the 0 power is 1. 2 to the first power, to the 1 is 2. 2 to the second power is 4. And then when we do negative exponents, it means 1 over. So 1 over 2 and 1 over 4. All right, so where did these go? Well, we got 0, 1. We got 1, 2. We've got 2, 4. Whoa, that's 3, 4. 2, 4. We got -1/2, -1/4. And so basically we got this set of points here. If we went and did another point, it'd be 3, 8, which is all the way up here. Um, what the heck is this graph doing? Well, if we were to connect the dots, we would get something that starts to look like this. The question is, can we connect the dots? And what happens to the left? Because we go this way and we go a little further down. Well, does it go like this? Or does it go like this? Or does it just flatten? Well, what ends up happening, we have to remember, is that every time we take a step to the right, we do times 2. Because 2 to the third is 2 squared times 2. And then 2 to the fourth is 2 cubed times 2. So if we're doubling every time we go to the right, that means we're halving every time we go to the left. And if you cut a number in half, and you cut a number in half, and you cut a number in half, it just keeps getting closer and closer to 0. So what ends up happening, in fact, is we have what we call an asymptote. It's a fancy word that says, I'm not touching you, I'm not touching you, I'm not touching you. So this number here, this line here, this dotted line is called a horizontal asymptote. But the question is, are we okay to connect these points? Like, okay, so 2 to the first is 2 and 2 to the second is 4. Is 2 to the 1.5 equal to something? Is there a place where it equals 3? Like, okay, if I go to 3 here and there seems to be an x value that goes with it, but is there? Can I do that? It seems to me that we need to justify that it's okay to plug in between numbers. Well, let's not forget, we know how to do fraction exponents. A fraction exponent is a fancy way of saying a root. 2 to the 3/2 would be the cube root of 2 to the third, which is the cube root of, or the square root rather, square root of 8. So those are values, and we can make them up, and we can use any fraction we want here. And if we use enough different fractions, we will end up with a result of every number between 2 and 4. So is it legit to do this? Yeah, in fact it is. We can connect these points up. So there is going to be an x value for every y and a y value for every x as we move across. That's important for establishing that this is a connected function, and also later when we decide it has an inverse, nudge, nudge. But this is loosely speaking what y equals 2 to the x is going to look like. So do other exponential functions look like this, or is it just 2 to the x? Well, let's consider then, what does y equals 3 to the x look like? And we'll use the same set of values. If we do it with 3 to the x, we still go to 0, 1, but now 3 to the first is 3, 3 squared is 9, we got a 1/3, we got a 1/9. So what happens? We go 0, we go 3, we go 9, we go 1/3, we go 1/9. It basically is the same graph. It's just more extreme. It shoots up to infinity like a polynomial would, but it does it super fast, and it levels off to zero kind of faster as well, because that's 1 divided by whatever's happening on the right. So this is going to go really quick, and if we were to use a more gradual number than 2, it would be a flatter graph. If I did like 1.5, it might look like this or something like that. So what happens if we use numbers that are even smaller than that? What if we did like a half to the x? So what does y equals 1/2 to the x look like? Well, let's remember 1/2 is another way of writing 2 to the negative first, or in other words, 2 to the negative x. So we can use that to our advantage now. If we want to graph 1/2 to the x, let's think of it as 2 to the negative x, and let's consider what happens when we plug in those numbers. So first of all, plugging in a 1 is still going to give us, or a 0 is still going to give us a 1, because anything to the 0 power is 1. But now, if we plug in a 1, it's like we plugged in a negative 1 over here. So it's 1/2. And likewise, 2 is like plugging in a negative 2 to the blue graph. And this goes in reverse the other way too. So we end up with 1, 2 over here, 4 over here, but then 1/2, 1/4. So we end up with a shape that is in fact the mirror image of the one we had before. This got a little bit off. And so it is literally just the blue graph backwards. And if you know a thing or two about graph transformations, this shouldn't surprise you. So now we need to take a step back and talk about what do graph transformations do. So I'm going to flush all this in a second, but first I realize there's one important point I have to make here. Um, Graphs like 2 to the x and 3 to the x, which increase as we move left to right, are called exponential growth functions, which it isn't hard to see why. Graphs like 1/2 to the x, which decreases as we move left to right, is called an exponential decay function. And the reason we call it decay and not just like an exponential shrink function is because it ties very closely to a specific application that has to do with radioactive isotopes. So when we get into applications later on, we're going to see how that applies. But what's the difference? Well, the growth functions, they grow. And so I mentioned earlier, as we move to the right, we multiply by whatever the base is. Well, if we're growing, that means that our base is making us grow. So growth functions must have a base that is greater than 1. By contrast, decay functions, if they are getting smaller, they must have a base that is less than 1 and also greater than 0. We're not dealing with negatives. What about if it's equal to 1? 1 to the first is 1, 1 squared is 1, 1 to the third is 1, 1 to the fourth is 1, etc. If we did 1 to the x, it would just be a horizontal line. And 0 to the x would just be a horizontal line on the axis. We don't consider those possibilities. They are really not part of the scope of what we deal with. Those are trivial cases. But we do not use negative numbers. Negative numbers are going to do a weird thing where they ping pong back and forth. They go above the graph, they go below, they go above, they go below, and it doesn't actually connect. So because they behave really strangely, we don't deal with that. But we do need to differentiate between growth functions and decay functions. All right, so now I'm going to rewind. We're going to take away everything that is not the original 2 to the x graph, because now we need to talk about graph transformations. Oh, sure, we'll take out the title too. Why not? We don't need that stinking title, am I right? We know what this is about at this point. So graph transformations. We need to remember that in general, I can put that back. In general, when we deal with graph transformations, we say y equals a times f of b times x minus c plus d. And sometimes teachers will use h and k here instead. But what we remember about these is that a is the vertical stretch factor, b is the horizontal stretch, or compression would be more accurate, c is the horizontal shift, and d is the vertical shift. And it's important to recognize all of those things and how they behave because we're going to start using them. The one that you can kind of get away with not knowing is the b. B is not super important compared to the others, but we definitely need to know our shifts and we definitely need to know what the vertical stretch does. So let's consider if we were to graph y equals 2 to the x minus 3 plus 1. Okay, so we'll call this function f of x here. So what on earth is happening? Well, if we were to try to just plot points, this would not be a highly profitable strategy. We would go, all right, if I plug in a 0, 2 to the negative third, that's like 1/8, plus 1. All right, I have 1 and 1/8. And if I try to plug in a 2, 2 to the 2 minus 3, 2 to the negative first, or I'm plugging in a 1, excuse me. So 2 to the negative second is 1/4, plus 1, that's 1 and a fourth. And plug in a 2, 2 to the 2 minus 3, it's negative 1, 1/2. 1/2 plus 1, that's 1.5. If you don't understand all those, pause and write it out, and you'll see what I'm talking about. But if we go to these other points, we end up like 1 and a 16th, 1 and 1/32, and that doesn't really give us much to work with. We could keep going. We could find out that this is 1 and this is 2, but this is really not terribly helpful ultimately. What is more helpful is to look at this in terms of its parent function. If we look at it in terms of its parent function, what we're going to conclude is that our inside number is c. This is the thing that's happening within the function. So we're going to say that c, which is inherently subtracted, is equal to 3. And the number that we have tacked on to the end and added, d, is equal to 1. Okay, so what does it do? It means that we are going to move everything to the right by 3 and up by 1. And everything else is going to stay as it is, but we're basically going to take our blue graph here, if you will. Let's see if I can do this. I'm going to highlight it all, and I'm just going to move it over and move it up. And this is basically what our graph will look like. And yes, I realize I grabbed part of the brown text over here, but this is what we're aiming for. So how do we make that happen? Well, first of all, we need to move the asymptote. The asymptote is the easiest thing to deal with because, first of all, it only has one dimension. And second of all, because it passes through the origin. And so considering we want to compare everything against our, I'll call it our new origin, it makes sense to deal with the asymptote first. Well, moving the asymptote to the right by 3 does absolutely nothing. It's an infinite line. You shift it to the right, it's still an infinite line. It still goes on forever, but it does go up by 1. So our I'm not touching you line is going to go right here. And the graph is going to get closer and closer to this line. But now this line is elevated. It's off of the x-axis. Well, we went to the right by 3 and up by 1. So this point right here, I'm going to put a little x here. This is like our new origin. And from this point, we're going to graph all the same points. We're going to graph what would have been 0, 1, and what would have been 1, 2, and what would have been 2, 4 if we went from this spot, 3, 1, instead of from 0, 0. And likewise, we'll go to the left, negative 1, 1/2, and negative 2, 1/4. And if we do this and we connect, we should get something that looks very similar to what happened when I took the blue graph and I moved it over. Because every single point that we look at here, if we were to just compare these points, over 3, up 1, over 3, up 1, over 3, up 1, we've got over 3, up 1, over 3, up 1. If I took the 3, 8 and moved it, it would also do the same thing. So everything has translated 3 spaces to the right and up by 1. So if you want to do this, 2 ways to create this graph. The first is literally just graph the parent function and then move the points. I think that that's a really tedious way to go. I don't want to call it a lazy way, but it's not lazy because it involves more work, but it's not a very intense way of thinking of it. It's just a very dry, all right, let's pick these points and move them. But you can see that that's in fact exactly what we did, moving from the blue to the green via those pink arrows. The other way is to decide where your origin is and graph normally from there. And so that's kind of what I'm doing here is I'm saying, okay, well, I am working off of this is now like my x-axis and this is now my y-axis. So when I come from here, this is 0, 1, and this is 1, 2, and this is 2, 4. So I wasn't clear about what I was doing before, hopefully that clarifies that basically I'm just saying let's pretend we drew a different set of axes on top, and in the blue, this is where our points go. And we created that by following the numbers and what shifts that they create. All right, clear as mud, I'm sure. But now let's erase a whole lot of this stuff. I'm going to remove basically everything except our cheat sheet for the graph transformations. So hopefully I'm safe to just highlight and erase now. We're going to do another one. So I'm going to ask, what does y equals 3 to the x plus 2 minus 1 look like? Well, we got to think about this carefully. First of all, our parent function is going to be 3 to the x. That's when we don't have any sort of movement, any sort of weird stuff going on. We do have that 3 in there, and you might want to be tempted to say that's one of the a, b, c, or d, but really, if we take away the 2 and we take away the 1, 3 to the x is a perfectly nice normal function that we can deal with. So don't get confused here. But then we've got the plus 2 up top. That is an inside number. So therefore, that is a horizontal shift, a c value or an h value of -2. Remember that this is written as x minus c, not x plus. So x minus -2 is the same thing as x plus 2. So shift 2 to the left. We also have a -1 out back, which is a vertical shift, or the d value, of -1. So we're going to shift 1, we're going to shift down by 1. And this is basically our roadmap. We need to know what 3 to the x looks like, and then we need to move it. So if I were to sketch out the graph of 3 to the x, first of all, we need our asymptote, and then we need to go to 0, 1, because we always have 0, 1, at least in parent functions. And then we go 1, comma, our base number, which is 3, 1, comma, 3, and then 2, comma, the base squared, which is 9. And then we're going to go -1 is a third, and -2 is a ninth. And then we would be connecting those points. I guess I'll do that for demonstration purposes. But in this case, we've got some movement going on. We need to instead say, well, this graph, because we're going to go left by 2 and we're going to go down by 1, let's say that our new origin, as it were, is kind of right here. So first of all, let's deal with our asymptote. It goes down by 1 and passes right through our new origin. And second of all, from our new origin, we are going to plot the point 0, 1 and 1, comma 2. Not 2, I'm sorry, this is 3 of the 1, comma 3, and then 2, comma 4, 5, 6, 7, 8, 9. And we'll get 1/3 and 1/9. So the graph that we actually want is here in green. Not that tall. I'm trying to draw with my mouse, which is not a very precision instrument. Forgive me. So there is our 3 to the x plus 2 minus 1. So we can do this. It's not actually that big a deal, but it does require some practice. So obviously I'm going to do a couple more examples. I am, however, going to make them slightly more obnoxious because that's what I do. I'm a math teacher. So we're going to consider a couple other possibilities. The first is what happens if we deal with y equals 1/2 to the, and I'm going to say, no, I'm not going to do a negative x. We're going to say to the x plus 3 or plus 5, let's say, and then we're going to do plus 3. All right, so first of all, we need to remember that our parent function is 1/2 to the x. This is a decay function, so let's remember that we're dealing with decay here. It's 2 to the x backwards. Okay, now let's look at our numbers that are inside. We've got a plus 5 up here. That's our c. It's the inside number that's being added or subtracted. But normally c is written as subtracted. So we need to think of this as x minus -5. Therefore, c equals -5. And that means we are going to shift to the left by 5. And then our number out back is a plus 3. So d is equal to 3, and that means we're going to shift up by 3. So our base graph, our parent graph, would have had our asymptote, and it would have gone through 0, 1, but then it would have been a backwards 2 to the x graph. It would have been an exponential decay. And so it would look something like this. Trying not to draw horribly, but I'm also trying to draw with the mouse. So forgive the sketchy lines here. But what we actually want, we're going to go to the left by 5 and up by 3. All right, well, up by 3 is still going to be up by 3 with the asymptote. That's easy enough. But our new origin point is right here. So we need 0, 1, and 1, 1/2, and 2, 1/4. And if we go to the left, we go to 2, and then we go to 4. And I'm going to do my best to connect these now. And so it's going to look something like this. Obviously, the graph that I have is not well suited for this particular domain, but there's what our graph looks like. And oh, by the way, yeah, we should talk about that domain and range thing, shouldn't we? Because teachers love domain and range for some reason. I don't know why. It's not really all that interesting. But domain of an exponential function, unmodified, meaning a parent function. As you can see, we can plug in any number we want, and there's a value going all the way across, whether this is a decay function or it's a growth function. So therefore, our domain is all reals, which you can write as the fancy R thing, or you can write it as -infinity to infinity in this interval notation. Or is that set notation? I get them confused, whichever that is. Okay, so that's domain. What about the range? The range of an exponential function, unmodified. Well, look at our green graph, because that's an unmodified parent function, right? We can have pretty much any positive number, right? but we can't have 0. We never touch 0, and we certainly never have a negative number. So this is all positive numbers, or we could say y is greater than 0. The more proper way, usually we're going to write 0 to infinity. And we're going to write this with a parentheses because we don't want to include 0. Infinity is always written with a parentheses, but if we had written this with a bracket for 0, that would have meant including 0, which we don't want. So there's our general domain and range. What about for this particular graph? Well, for the modified, we're going to go to the left by 5 in this case. This is unchanged. Because it was infinite before, it's still infinite. So nothing happens, basically. But our range, well, we did have a bottom end, and that bottom end is moving up and down. So in this case, it's d to infinity. It goes up by d. So therefore, 0 plus d is d. Infinity plus d is still infinity, hasn't changed. So this is basically what we're going to expect. Now, there is possible to do a vertical flip, and we're going to see that in just a second. But basically, this is the idea of what we're dealing with when it comes to domain and range. Personally, I think domain and range are a silly thing to get into, but there is a reason to discuss them, and that is for when we start doing log graphs. Given the rate at which this video is going, I may need to break that up into 2 videos because we're going really slow here, going through all these examples by necessity. But hopefully nobody has any questions about any of that. A lot of these things I am going through pretty quickly, though. I'm skipping over a bunch of understandings along the way, which is, looking at the parent functions and graphing a bunch of parent functions and really taking in the parent functions. Hopefully your teacher did a bunch of those, and this is just reinforcement. But we're going to do some different shifts now. So let's say we got y equals, and I say 3 times 2 to the x minus 2. All right, so it's minus 2 in back. It's an add or subtract on the outside of our function. So that means that our d or our k value is negative 2. And we are going down by 2. This 2 is just the base. But this 3 is not an add or subtract. It's a multiply. So that means it's an a value. This means we are stretching by a factor of 3. So everything is going to get 3 times as tall as it would have been. So what does that mean? Well, let's draw our parent function. Once again, I'm going to draw the parent function. Once you get good at these, you can skip the parent function. You'll just kind of have an idea of what this looks like. But for right now, we need to see our parent function. And so we've got this and this and this, and it's going to do something like that, right? Okay, so first of all, we have to remember that everything is down by 2. So we better move our asymptote. And if we only moved our asymptote, we would be here, and we would be here, and we would be here, and then we would have the exact same thing as our blue, or green rather, except it would be down. Here's the problem. We have to do a vertical stretch. So in order to deal with this vertical stretch, which I'm going to do in pink, what we have to think of is everything is going to be 3 times as far off the line. So whereas this point right here is 1 off the line, it's now going to be 3 off the line. This point was 2 off the line, so now it's going to be 6 off the line. This was 4 off the line, so now it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, just made it. 12 off the line. 1/2 here is now going to be 3/2 off the line. 1/4 is now going to be 3/4 off the line. So now if we connect our purple points, or pink points, I guess they are, we're going to see that we have a much, much taller graph, or much, much steeper graph. The funny thing is that this actually looks the same as if we just shifted this graph to the left a bit. And that is, in fact, actually the case for reasons that I can prove. But what we really want to think of is not that we're moving to the left, but rather that we are making it taller, that the height off the line is just 3 times as much as what it was before. And so when you see a vertical stretch, meaning that number in front, you need to go more off the line. And while normally the line would be the x-axis, in this case, it's going to be our new x-axis, which is where the horizontal asymptote is going to lie. Great, fantastic. That's absolutely clear as mud, I'm sure. Let's do one more. Let us try instead. Let's talk about y equals 2 to the x minus 3 plus 3, but we're going to multiply this by, let's say we multiply it by 1/4. So what's that going to do? Well, we've got an h value or a c value of 3. We've got a k or d value of 3. So we're shifted 3 in both directions. 3 over, 3 up. But we've got this a value of 1/4. A equals 1/4. So we know we're going to the right by 3. We're going up by 3. But we're also going to stretch by 1/4. That means that this function is going to get shorter. So whereas our most basic graph, where we do our parent function, we're going to go through 0, 1. We're going to go through 1, 2. We're going to go through 2, 4, and -1, 1/2. I'm just doing a quick and dirty version here now because we're trying to skip past this step a little bit. If we did the shifting, 1, 2, 3, 1, 2, 3, okay, there is the new origin. And so there is our asymptote cutting right through it. And we go to 0, 1, and we go to 1, 2, and we go to 2, 4, and -1, 1/2, and -2, 1/4. And it would look something like that. But again, we also need to consider the 1/4. So in using this 1/4, we're going to go 1/4 as much off the line. So this is not 1 off the line, it's 1/4 off the line. This is not 2 off the line, it's 1/4 of that, which is 1/2 off the line. This 2, 4 point is not 4 off the line, it is 1 off the line. And so everything's going to get really flat. The next point, which would have been 8 off the line, is now 2 off the line. And so we end up with something like this, which again, as I said before, is going to resemble just doing another horizontal shift. Now, why is that? Well, let's consider the math on this specific instance. 1/4 times 2 to the x minus 3 is the same thing as 2 to the -2 times 2 to the x minus 3. And if I were to use my exponent properties to put these things together, this would be equal to 2 to the x minus 5. So if I basically absorb this vertical stretch into the exponential, I now have a c value of 5. And that's very similar to if I had started right here and done the graph, isn't it? In fact, it's exactly that. So the reason why it looks like we're doing a horizontal stretch is because basically, or shift is because basically we are. All right. So there are cases where we have an a value, but there's one more wrinkle that we need to see. No, it's not with a b value. I'm not actually jumping into that. I want to talk about what happens if we say y equals 9 minus 2 to the x. Oh, what is this? Well, let's rewrite it as -2 to the x plus 9. And if we rewrite it this way, the plus 9 is tacked onto the n, that's the d value. We're going up by 9. That's a big vertical shift. We're going way off the top, aren't we? Except not really, because the number in front, this is like saying -1 times 2 to the x. Do not confuse this with -2 in parentheses to the x, which is something we don't graph. This is just -1 times 2 to the x, because order of operations tells us we do exponents before we do multiply. So we have an a value of -1, and that means we are stretching vertically by -1. It is -1 times as tall as it would have been. -1 times as tall? How do you get -1 times as tall? Well, it means instead of coming up above the ground, we're going to go down into the ground. So first of all, let's do our shifting. We're going up by 9. So our horizontal tangent line is all the way up here. And the point where we would start to graph is right here. That's that point that I kind of drew a little X on called the new origin. All right, now our parent function would normally go to 0, 1 up here, but we're not going to go to there. We're actually going to go down by 1. And we would have gone up to 1, 2. Instead, we're going to go down to 1, 2. We're going to go down by 4. We're going to go down by a half. We're going to go down by a quarter. And what we have done is we've created a vertical flip. And if you remember from your parabolas or from any other kind of graph shifting, that when a is negative, the graph will flip vertically. Incidentally, when b is negative, which we don't talk about a whole lot here, but if we need to, the graph will flip horizontally. And we saw that when we shifted between 2 to the x and 1/2 to the x, because 1/2 to the x was 2 to the negative x, and it represented a horizontal flip. I mentioned earlier that I would prove it, and that's the argument that I'm going to use. So if we have a negative on the inside, it's going to flip in the other direction. So what does that look like? Well, let's suppose I said y equals, so versus 2 to the x, we have 2 to the negative x plus 9. 2 to the negative x plus 9, well, I'm going to have to move this text over here because it's going to be in the way. We're still on the plus 9 thing, right? We still have a d value of 9. So we're still going to be up by 9. We're still going to have the same starting point or same origin, as it were. Well, we got 0, 1, but then instead of going to 1, 2, we go to -1, 2. So going to 2, 4, we go to -2, 4. And again, everything is flipped around. So this is also backwards of what a parent function of 2 to the x would look like. We could have both of these things happening. We could, in fact, do y equals 9 minus 2 to the negative x. And now we have both flips. So what does that look like? Well, it's the red graph, but turned the other way. So I'm just going to shortcut a little since we already know what that looks like. And we're going to flip the points to the other side of the axis, and we're going to connect up. So we will have something that looks like that. So there is a rundown of everything that you might see with an exponential graph. Isn't that lovely? We still have logarithm graphs to talk about. Oh boy, how long is this video going to be? Well, I'm glad you asked that question. Hopefully not as long, but we now need to turn this graph the other way because logarithms are inverses. And what you may recall about inverses is that they are a reflection across this diagonal line that I just drew right here of y equals x. So if I graph y equals 2 to the x, that goes through 0, 1 and 1, 2 and 2, 4 and -1, 1/2 like this, and has a horizontal asymptote out here, well, then y equals log base 2 of x, which is the inverse to that specific exponential function. First of all, instead of 0, 1, it's going to be at 1, 0. Instead of at 1, 2, it's going to be at 2, 1. Instead of 2, 4, it's going to be at 4, 2. It'll be at 1/2 -1. And instead of having a horizontal asymptote, it's going to have a vertical asymptote. I guess I could call it a tangent line, but it's an asymptote. And so the graph of this is going to look something like this, basically. And if we're going to play the domain and range game again, The domain of this now is flip-flopped from before, so it's 0 to infinity, and the range is all real numbers. So if we're going to talk about logs, well, this is what your parent function looks like. So we need to remember that for an exponential, you're generally going to graph 3 key points if you graph nothing else. You're going to graph 0, 1, and graph when x is 1, y is whatever the base is, and when x is -1, y is 1 over the base. So in this case, it was 0, 1, 1, 2, and -1, 1/2. And if you graph no other points, your teacher will probably be happy with these 3. Well, what about for the log? Well, log is just when you flip-flop the x and y because it's an inverse, and that's how we find inverses. So that means when y is 0, x is 1. When y is 1, x is b. And when y is -1, x is 1 over b. And you can see clearly that that's exactly what happened because our base is 2. We went to 1, 0. We went to 2, 1, and we went to 1 over 2, -1. So there's our parent graph. So if you need to know how do I graph a logarithm, that's what it's going to be. So let's do away with our exponential, but let us graph one other parent graph just to make sure we understand. So I'm going to move this out of the way, but I'm going to keep the purple or the brown one on there. Let's talk about y equals log base 4 of x and what that's going to look like. So in this case, where b is equal to 4, our points of interest are going to be 1/4, -1, and 1, 0, and 4, 1. So we still have this point right here that hasn't gone anywhere, but now we're going to go to 4, 1, and 1/4, -1. And just like when we graphed with a stronger base for the exponentials, with the logarithms, it's also going to be a stronger effect. It's just going to be twisted the other way. If we had graphed 4 to the x, it would have looked something like this. Again, just graphing those 3 key points at 0, 1, 1, 4, and -1, 1/4. And apologies for that being horribly sloppy. So this is essentially what we're going to do when we graph logarithms. And then when we do our shifting, we're going to use all the same ideas. So let's suppose that we graph y equals log base 3 of x minus 5 plus 2. All right, so let's graph our parent function first of all. If we were to graph the parent function log base 3 of x, we're going to have this asymptote here on the axis, but it's a vertical asymptote now. We would go through 0, 1. Our base is 3, so we go through 3, 1, and we would go through 1 over 3, -1. And we would connect, something like that. But we need to be a little more interesting now. We got to go to the right by 5 and up by 2. Is that what those numbers do? Well, the -5 is an inside number. It's being added or subtracted. So this is definitely C. And this right here is an added on the outside. That's definitely D. So yeah, that's exactly what's happening. We're going to go to the right by 5 and up by 2. So our new origin is right here at 5, 2. Well, the first thing that I told you to move with the exponential graph was the asymptote. So let's move our asymptote. It goes to the right by 5, but it goes up and down by 2. Up and down by 2 isn't going to do anything. Up and down for a vertical line is just going to extend forever. So we're only moving it to the right by 5. And there we go. And now we're going to graph the same points from here. We're going to go to 0, 1. We're going to go to 1, 3. We're going to go to 1/3, -1. And now we will connect these. And this will go down, down, down forever. It will never actually touch the purple line. It just hugs it very, very closely. So this is what y equals log base 3 of x minus 5 plus 2 is going to look like. All right, so that's shifting. What happens if we get into stuff that incorporates a vertical stretch or a horizontal stretch, though? So what if I said y equals log base 3 of 6 minus x? All right, let's rewrite this, because written like that doesn't make a whole lot of sense to us. It's negative x plus 6, which I'm going to rewrite one more time to be extra careful here. It is log base 3 of negative x minus 6. And yes, it is absolutely essential you do this second thing and factor out this negative from these. Because if you don't do that, you don't get the correct c value. C is our added or subtracted on the inside. C is equal to 6 here. But now we've got a negative 1 times on the inside. That means b equals negative 1. So we are going to the right by 6, but we've got a horizontal flip because that's what a negative b value does. This is a little more gross. I stuck with the log base 3, so we got the same parent function, but we got to go to the right by 6. 1, 2, 3, 4, 5, 6. That's going to pass through here. So there is our vertical asymptote. And now we got to draw the graph backwards. So 0, 1 is now, or 1, 0, excuse me, is now negative 1, 0. 1, 3 is now, or 3, 1 is now negative 3, 1. And 1/3 negative 1 is now flipped to the other side as well. And so we have a graph that's going to face this way. Obviously, if you have to answer domain questions, it's going to be everything to the left of our asymptote instead of everything to the right. Likewise, if you had a vertical flip on the exponential, that's also going to affect the range. So make sure you watch out for that. All right, so there's 1. So let's clear this. And now let's do one other. Let's suppose I ask you to graph y equals negative log base 2 of negative x plus 1 plus 2. And this is going to be the granddaddy question. It's going to tie it all together because this is a lot taking in here. All right. So a is negative 1 because we have a negative 1 multiplied on the outside. B is negative 1 because we have a negative 1 multiplied on the inside. C is negative 1 because this is like x minus negative 1 on the inside here. And D equals 2. All right, so they couldn't all be negative 1. I mean, they could have been. I could have written minus 1 here, but let's not do that. So we need to go to the left by 1. We need to go down by 2. But then we need to do a horizontal flip and a vertical flip. Okay, one thing at a time. Let's start with our asymptote. The asymptote is 1 to the right, or to the left, your other right. Okay, so where's our starting point? Well, it's over 1 down by 2. It's right here. So normally we would plot 0.01, except it's horizontally flipped. So lol, no, it's over here. The next point we would have graphed would have been 1, 2, or 2, 1 rather. Let me say it correctly, right? X, y, it's equal to 0, 1, and 1 comma base, and negative 1, 1 over the base for the exponential. So the log is the other way around. Let's not confuse these. I'm going to rewrite this just to demonstrate, because if I'm messing them up, then obviously you're going to as well. So what would have been 2, 1 is now going to be flipped around because we're making everything backwards what it would be. So it's actually -2, -1. All right, so -2, -1 is like right here. I'm gonna go back to blue. And our other point would have been at 1/2 comma -1. So now it's -1/2, -1. And when we connect this, it should look something like this. Oh, well, that looks like an exponential graph the way it curves, doesn't it? It looks an awful lot like an exponential graph, but this is definitely not an exponential graph. Why? If you didn't know what the function was and you had to say, what is this the equation of? What do you notice is here that is not part of an exponential graph and vice versa? It has nothing to do with the curve itself and everything to do with the other thing that we drew on the graph. I'm referring to the vertical asymptote. It has a vertical asymptote rather than a horizontal one. This means it must be a logarithm graph. That's not to say that logarithms are the only graphs that have vertical asymptotes. I can draw others like 1 over x. But as far as exponential versus log, we're dealing with a logarithm that's kind of masquerading as an exponential. So if you had a teacher that was making you go the other way and saying, here's a graph, what is the equation for it? First thing you want to look at every single time is going to be the asymptote. And then you look at, am I flipping around? And then you look at the shifts involved. So let's do an example of that, and that'll be the last thing that we do. And then we can finally lay this video to rest here. So if I draw a graph for you and I ask, what is this the graph of? So I'm going to draw this. And then I'm going to start here with this 1 point off the line. And I'm going to go here. And then I'm going to go way up here and there. And I'm going to say, what is this graph? So the very first thing you have to ask yourself when you're doing a graph identification question is it an exponent or a log? So you're going to look at the asymptote. So in this case, we have a horizontal asymptote, so it's exponential. Okay, groovy. Next, we need to say, what's the shift? Or so first thing we need to do is pick a starting point. Ideally, if we can, a point that is 1 off the line. So if I notice this point right here, let me grab a different color. This point right here is 1 off the line. So we're going to use this as our point of reference, and we're going to say that our new origin is right here, and this is the new 0, 1. If this was a logarithm graph, we would do the same thing, except we would go in this direction. So it means that step 2, pick a starting point. Now, there is no wrong or right answer to this technically. You could have picked one of these other points. So if you said, but I wanted to use this point over here at 4, -1, okay, you can do that. Because as we go through the rest of these steps, you're going to see that it will result in something equivalent. All right, step 3. Determine the shifting. So how far did we go to the right and how far did we go up to get to this new, our new starting point, our new origin? So we went to the right by 3 and we went down by 4. Notice I'm going to the asymptote and not to the point that we chose. So we picked our starting point. Our starting point was 3, -3. We went to the right by 3, down by 4. So C equals 3 and d equals -4. Okay, and then we need to ask, is there flipping? Horizontal will lead to b is -1. Vertical will lead to a is -1, or just negative in general. It could be a negative something else if we also have a stretch in addition to a flip. In this case, there's no flipping. No flip. The other question we have to ask is there stretching? Now, this will be based on the point that you picked. We picked a point that's 1 off the line. Our starting point when we do these wants to be 1 off the line. Off the line, so no. Therefore, we will conclude that a is 1 and b is 1. There is, however, one last thing we have to consider. We don't know what the base of this function is. Go to the next point over to determine the base. So you'll notice when I picked our starting point here that was 1 away, we can go to our next point over and we can note that while this is 1, this is 3. So our scaling factor is 3. The next point is 3 times as far as the previous one. So the base is equal to 3. Okay, now we are ready to finally write this thing. According to our last bit of information, our parent function is 3 to the x. We are shifted, we have a c value of 3, we have a d value of 4, and although we don't need to write them, a is 1 and b is 1. So I'll write those in blue to say, yeah, we don't actually need those, but for point of emphasis, there they are. Okay, let's do one more. And then hopefully that will get the idea. Obviously, 2 examples are probably not enough by themselves, but you have been seeing this in class ideally, and this is just extra reinforcement to the idea and the way that I'm presenting it. So I'm going to draw another graph, and I'm going to draw it like this. This one's going to be a much harder example, by the way, because I'm going to get fancy. We're going to go, let's say, here, and we're going to go here, and we're going to go here. And now we're going to try to create this thing. All right, what the bleep is this? Well, step 1, exponent or log. We have a vertical asymptote. Therefore, this must be a logarithm. Step 2, we need to pick a starting point. All right, let's pick a starting point. Well, there isn't a point that's 1 off the line. We have this point here, which is kind of 1.5-ish. We're not sure exactly. This is somewhere in the middle. We're not sure. This one is very clearly 3 off the line. So I'm going to go with this one just because I'm pretty confident that this length here is 3. So the point that we're going to choose in this case is going to be 1, -2. You could have picked the other points if you're comfortable working with those, but I like this one because it looked most likely to be an integer for both the x and the y. All right, shifting. Well, we're to the right by 1. So, actually, I'm sorry. We're not to the right by 1. We're to the right by where our asymptote is, because the spot on the asymptote that aligns with this is actually our starting point. And of course, we're always shifted by the amount that the asymptote is. So in this case, it's right by 4. And based on the point that we chose, it's down by 2. That one will stay based on the point. All right, so C equals 4, D equals -2. All right, awkward, but here we are. Now, is there flipping? Well, a normal logarithm would have probably looked something like this, but we're over here. So is there flipping? Yeah. In which direction? Horizontal flip, so B is negative. A is still positive because we didn't flip the other way. All right, is there stretching? Well, in this case, there is because we're not one off the line. Yes, our chosen point is not one away from the asymptote. Asymptote, it's 3. Therefore, we have a horizontal stretch factor of 3. I guess I will end up talking a little bit about B after all. If this was in the vertical direction, we would have an A value of 3, and therefore A is just straight up 3. But the thing we have to watch out for, B is a little weird. B is weird. It's backwards. When I say B, I'm talking about B as in like the ABCD, not B as in the base of the logarithm. It's backwards. So we actually need this number to be 1 over. B is going to be 1 over 3. It's a really awkward thing that happens, but we're going to conclude, therefore, B is equal to 1/3, but oh, it's not actually 1/3 because of our previous conclusion, it's actually negative 1/3. Yes, like I said, this is going to be a question on steroids. There's a whole lot going on here. All right, and finally, we need to determine what our next point is. Well, by next, I'm actually going to go to a previous point, which is this one. I'm going to say, well, this is like 3/2 off the line versus this one being 3 off the line. So it looks like we're scaling by a factor of 2, right? 3/2 is times 2 is 3. So we are scaling by a factor of 2. Therefore, the base of our logarithm is 2. All right, now we've got all this stuff. So y equals log base 2 of x. But now we need to add in the goodies. All right, our c value is 4, so we need a minus 4. Our d value is minus 2, so we're going to subtract 2 out here. And our b value is negative 1/3, and that needs to be in parentheses. So there's our finished product. Okay, I am sure that this is all very, very confusing. I don't know how confusing it is. I don't know which parts are going to be confusing for you. So if you've watched this video and you've enjoyed it, but you're still a little bewildered, please leave a comment. Please let me know what worked for you or what didn't, so that I can update this, so that I can put an addendum, so I can do an entire video, maybe devoted to just one type of question that showed up here and that we can see in much greater detail so that it can be clarified. Thank you.